Hi, I'm Dan Abel, and in this lesson, we're going to perform calculations with current, voltage, and resistance using Ohm's law. So before we start to perform calculations with Ohm's law, it's important to understand why this equation or relationship is so important. Ohm's law is an important relationship because it allows us to relate three key quantities in a circuit. The current, which we talked about in a previous lesson, the resistance, which is how much the circuit or part of a circuit hinders the flow of charge, and the voltage, what's driving the flow of charge. That's our potential difference between 2 points. One common point of confusion when we're looking at voltage is this term electromotive force. And this was discussed back in the potential difference lesson, but it's worth reminding ourselves here that electromotive force and voltage are related, but in a circuit, they're not the same. The electromotive force is the number that's stamped on the side of a battery. So if you get a AA battery, it's going to say 1.5 volts. And that is how much voltage you would measure if that battery was not connected to anything. As soon as you connect that battery to the circuit, the voltage is going to drop slightly due to the internal resistance of the battery, which we'll talk about in a later lesson. So the key takeaway here is that the EMF is equal to the voltage of the battery when no current is flowing. The other key thing to remember about your voltage source, whether it be a battery, whether it be plugging into the wall or another source of voltage, what that voltage source is providing a high and low potential point for the circuit. And a conventional current, just like water flowing from a high point on a hill to a low point on a hill, the conventional current is going to always flow from a high voltage point to a lower voltage point. So, in a sense, we can think of the conventional current as just flowing down its concentration gradient from a high voltage to a low voltage. And since our voltage is what is driving the flow around the circuit, it makes sense that for a given resistance, as you increase the voltage, you will get a higher current. To use a water analogy, if you think of the voltage source as your pump, as you increase the size of your pump, you will end up getting more flow around your system of pipes. Resistance is measured in ohms, so more ohms, more resistance, less current flow. And this is captured in the Ohm's law relationship, delta V equals IR. So we see here that if the voltage goes up for a given resistance, the current will go up with it. But generally, the more common thing we have is a set voltage. Voltage is determined by the voltage source. So if it's a 1.5 volt battery, the voltage is set at 1.5 volts. So generally, the voltage is set, and as we change the resistance, the current changes inversely. So if your resistance goes up, your current will go down. But regardless, the key takeaway here is if you have two of the three of these, current, voltage, and resistance, you can calculate the third using Ohm's law. Let's apply this to a couple of practice questions. A says how much current will flow and in what direction when a 1.5 ohm light bulb is connected to a 9 volt battery. We have delta V equals IR. We have a 9 volt battery, 1.5 ohms of resistance. And so we want to know how much current will flow in this configuration. So we'll just divide 9 by 1.5, and we'll get a current here of 6 amps. So a 9 volt battery will push 6 amps of current through a 1.5 ohm resistor. As far as direction, by convention, the current will flow from the high voltage or positive side of the battery to the low voltage or negative side of the battery. Let's look at another question. In B, we have the resistance of a circuit cut in half and the voltage is doubled. What will happen to the current? So now we're going to use some proportional reasoning with Ohm's law. So if we cut the resistance in half, so we're going to have 1/2 the resistance. Cutting the resistance in half will double the current. So if you have 1/2 R, you will have double the current. Those are inverse to each other. But if you double the voltage, then you will also double the current because those are directly proportional. So if you do both of these things together, we'll multiply the effects and we'll get 4 times the current. So by cutting the resistance in half, you're making it easier to flow. By doubling the voltage, you're pushing harder. Both of those things together will increase the current by a total factor of 4. In a later lesson, we'll see how to apply Ohm's law to a full circuit in various places. But the key takeaway here is you can always relate current, voltage, and resistance using delta V equals IR.